Hello dear students, we saw the introduction of tree data structure. Now we are going to see the types of tree data structures in tree data structures. So there are different kinds of trees in data structure. The first one is general tree. So the general tree is a type of tree where there are no constraints on the hierarchical structure. So no constraints in the sense you can have any number of parent cells, any number of children cells. So any number of ancestors, siblings. So as you can see here, C1, the C contains any number of C, 1, 2, 3, 4, 5 leaf nodes. So there is no constrictions, there is no constriction in any sort of constriction in the hierarchical structure. That is the general tree. So next, moving on to the next type of tree, we have binary tree. So binary tree is something, each and every node must have at least 2 nodes. 2 children, that is, it can have a 0 children, it can have 1 children, it can have 2 children, but not more than 2 children. That is a binary tree. So you can see here properties, it follows all properties of tree data structure. Binary trees can have at most 2 child nodes. So it can have only 2 child nodes, not more than that. For example, now you have this is A, this is B, this is C node, and this is one node. So you can see that here is the tree node A and this is B, C, D, E, F. Now you can see this P node, this is a parent node which has 3 childs. So this is not a binary tree. So this is not a binary tree. So what is the condition is, it can have the leaf nodes, the whatever the node which ends should have 1 or 2 trees. Okay. Okay, moving on to the next slide. This is about the binary tree. So how to represent a binary tree? There are 2 methods to represent a binary tree. The one is array representation, the other one is linked list representation. Now we have taken a small example, that is A, B, C. This is one binary tree with n number of nodes. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a binary tree which comprises of 10 nodes. So using this node, let us represent a tree. So first let us see the array representation. So usually for array representation, we use a one-dimensional representation. So you can see here the sequential order of array representation. So as you can see here, so this is A followed by B, followed by C, followed by D, F, G, H, I, J. So you can see here, sorry, this tree has to be taken. First A is the root, you have to traverse from A, then B, then C, D, I, J, then F, then G, then C, then H. You can see here, once it ends here, it doesn't have any left child and right child. So that is why there is a 2 space here. Can you see this? After J, there are 3 spaces here. That is the reason. After J, F does not have any child nodes, there is 3 spaces. Again, G doesn't have a right child, that is why there is one more space. Then this is K, then C. After K again, H doesn't have any child, that is why this spaces. This is how you represent an binary tree in an array, that is in one-dimensional array. Now they say to represent a binary tree of depth n, using array representation, we need one-dimensional array with the maximum size of 2n plus 1. So if the array is of depth n, the maximum size of an array required is 2n plus 1. This is the array representation of a binary tree. Moving on to the next representation, we have a linked list representation. To represent a tree, what we use is, we use a doubly linked list. Doubly linked list is nothing but, it has 3 fields. The first one is holding a data. It has left child address and the right child address. The left child address holds the node which comes in the left side of the tree. The right child address holds the node which comes under the tree with the right side, towards the right side. Now can you see this? The same tree which I have taken in the example, the previous, the same tree is being represented here. So for this, first we have taken A is a root node. The A is a root node with the left address and the right address. Now A is connected to B and A is connected to C. B is connected to the left link and C is connected to the right link. So again B is a parent of D and F. Now B is connected to D from the left link Okay. Then F is connected from right link of the B. Now F doesn't have any elements, so both the link we mark it as null. Now moving on to D, D is again having two elements, two child nodes, that is I and J. These are leaf nodes because they don't have any child, that is why they are called as leaf nodes. Now both the address locations are made as null because they don't have a child node. So again K is a leaf node, F is a leaf node, H is a leaf node, that is why we mark both the address as null. Now G holds a K element, that is K child in the right side, that is why we link this through right. So this is the doubly linked representation, that is linked list representation of a binary tree. So you have to remember that binary tree is the collection of nodes where each node has at least two nodes. Okay, either you can have a 0. For example of binary tree, this is a binary tree, this is a binary tree, this is a binary tree, this is not a binary tree because the last node holds 3 child nodes, this is not a binary tree. Okay. So this is a representation of a binary tree using two methods, that is array and linked list. Okay, moving on to the applications of binary tree. This can be spoken at the last, but I'll just brief it out. So we will be using binary trees for searching algorithms. So there are many searching algorithms. So you can just use them for searching elements when you have n number of elements. It is very useful to search the elements efficiently. So next one is sorting algorithm, then we have database system, then we have file system where you can store the node and node in form of files, directories. So next is compression algorithm, then decision trees, then artificial intelligence gaming. So all these are applications of binary tree. So moving on to the next slide, this is a real time application of a binary tree. So we will be using binary tree in HTML, then file explorer, then it is used as basic data structure in Microsoft Excel and spreadsheet, then editor tool like Microsoft Excel, then evaluating an expression and routing algorithms. These are some basic applications of binary tree. Okay. So advantages and disadvantages, we can discuss it later. Now the most important part is here, the types of binary tree. So there are many types of binary tree. The first one being full binary tree, or you can also call it as a complete or perfect binary tree. Okay, is it full or perfect binary tree? Okay. Now, what is a full binary tree? A full binary tree is a special type of binary tree in which every parent or an internal node has either 2 or no child. So you can see the tree over here. The first is a root node, 2 and 3 are the child node. So root node contains either 2 or no children. So it should have 2 children or no children. Okay. So the first node is one is having 2 children, that is 2 and 3, 2 is having 4 and 5, 5 is having 6 and 7 as the children. Okay. So this is full binary tree. So nothing should be left alone. It can have a 0 or 2 children. So for example, if I take the same example, 1, 2, 3, sorry, this is 4, this is 5, this is 6. This is not an example of fully binary tree. Why? I will tell you. This is root node, it has got 2 children as 2 and 3. Okay. So this is a full tree. Now 2 is having 4 and 5, it is again a full binary tree. Now here 3 has only one child. What does the definition say? This root or parent node has either 2 or no children. So it should not be having this. If this is not there, then it is a fully binary tree. Okay. Okay. Sorry for that. Okay. Moving on to the next. Okay. Now perfect binary tree. What do you mean by perfect binary tree? This is again a type of binary tree in which every internal node has exactly 2 child nodes and all the leaf nodes are at the same level. This is perfect binary tree. So what is it? All the levels must be complete. They should have 2 child nodes. This is 1, The parent node has 2 and 3, it has got 2 child node. 2 is again having 4 and 5. So again this is 2 child node. 6 and 7 are the child node of 3. So what are they telling? Perfect binary tree is a tree which every internal node has exactly 2 child nodes and all the leaf nodes are at the same level. Okay, if at all I have some like 1, 2, sorry, this is 3, this is 2, this is 4, this is 5. This is not a perfect binary tree. What does it in definition say? It should have exactly 2 child. So even this should be filled. So all the levels, So all the levels must be equal or same. That is why this is not a fully perfect binary tree. This is a perfect binary tree. Okay, this is one more example of a type of binary tree. Moving on to the next is complete binary tree. Okay, what is complete binary tree? There are 3 properties, or you can just say through full binary tree but with 2 major differences. So there are 2 major, it is a fully binary tree. So what is the definition of fully binary tree? All the child nodes, so whatever the parent node must have 1 child or 2 child, not more than that. So that is a fully binary tree. So it is satisfying the fully binary tree, but still there are 2 major differences. The first one is every level must be completely filled. So something like perfect binary tree. So there should be equal amount of nodes in all the levels. 0, 1, 2. Now 0 has 1 element, 2 has level 2, this is level 1, this is level 0, this is root node, this is level 1, this is level 2. So they are telling every element must be completely filled. Okay, all the levels must be completely filled. So there should not be any leaf node. So all the leaf element must lean towards the left. So this should be left, whatever element, everything should be in the left, not on the right. The last leaf element might not have a right sibling. A completely binary does not have to be a full binary tree. A strictly binary tree in which the number of nodes at any level I is 2i, then the tree is said to be complete binary tree. Now for a complete binary tree, you can also have this example. So this is 1, this is 2, this is 3, this is 4. This is again a complete binary tree. This is 5, this is 6. So whatever node, the leaf node should be towards the left, it should not be towards the right, and it has to be complete. So all the complete binary tree need not be a full binary tree. So this is the definition of complete binary tree. Now you can see here level I is equal to, if level I is equal to 0, the number of nodes is 2 raised to I, that is equal to 1. So you can have at level 0 only 1 node, at level 2 you can have 2 nodes, that is 2 to the power of 1, that is 2, then 2 to the power of 2 is 4. So at level 2 you have 4 nodes, then again similarly at level 3, so this is level 3, that is 2 to the power of 3, that is 6, then again 2 to the power of 4, it goes on. That is the formula for levels. So next is almost complete binary tree. This is strictly binary tree in which is not full only at the last levels. Okay, what are they telling is it is a binary tree, but it is not full at the last level. So you might not have any leaf at the last level. So last level is need not be full. That is what they mean here. They have taken one simple example here. Level I is equal to 0. The number of node is equal to 2 raised to the power of 5, that is equal to 1. So 2 raised to 1 is nothing but, this is 2 raised to 0. 2 raised to 0 is equal to 1. 2 raised to 1 is equal to 2. 2 raised to, see, it is not full. So you does not have 3 elements here. So this cannot be satisfied. Okay. That is what they are telling. This is strictly binary tree or almost complete binary tree. So the last level need not be full. That is what they are telling. So moving on to the next binary tree, this is degenerate or pathological tree. A degenerate or a pathological tree is a tree having a single child either towards the left or a right. You can see that in every level there are only single nodes. So 1 is a single node, 2, they does not occur in pair. That is what it is, degenerate or pathological tree. There are 2 types of degenerate or pathological tree. You can also call them as skewed binary tree. A skewed binary tree is a pathological or degenerate tree in which tree is either dominated by the left node or it is dominated by the right node. So, you can see here all these nodes are towards the left. This is all the nodes are towards the right. So, this is called as left skewed binary tree and this is called as right skewed binary tree. So, these are some type of binary trees. Okay, and one more is the balanced binary tree. It is a type of binary tree in which the difference between the height of the left. So, the difference between the height of the left and the height of the right subtree for each node is either 0 or 1. So, this and this tree and this tree, you need to identify the difference of that and you will be finding. So, this difference should be either 0 or 1, not more than that. That is what they say, that is, this is the balanced tree. Okay. So, we just saw the representation, binary tree representation. So, how do you write a binary tree using a see, this is the implementation part. You have to create a node using a structure, using what happens here. So, what are they doing here? This is a structure. So, structure is used, structure is what? Different type of data types, structure holds different types of data types. So, here we do struct node, this is creating a node, okay, struct node. So, one new node we are creating. Inside the node what do we have? I told you it is a doubly linked list, that is why we have got 3 fields. One is data field, left link and right link. Okay. So, that is what we are doing. We are taking one integer data, we are to store the data, we are taking an integer variable, then we are saying struct node is equal to pointer left is this one. So, this left is holding the address, that is pointer or address of the next node. This is struct node pointer right, this will be holding the address or pointer to the next node. This is pointing to this data, this is pointing to this data. These leaf nodes does not have any addresses, that is why both left and right are null. This is the struct, this is how you create a node using the struct. So, after this we have to allocate memory for the node using malloc function. So, malloc in C, but in C++ we will be using a new operator. Okay, dynamic memory allocation will be done. Okay. Okay. This is one more type of tree, binary search tree. Okay, what is binary search tree is nothing but, see, can you see that there is 45, 30, 50, 25, 35, 40 and 60. So, this is a binary tree, this is a root node, this is one subtree and this is one subtree. Okay, this is one subtree and this is one subtree. What is happening here is each node, the nodes which are towards the left will always have a lower value when compared to the nodes towards the right. So, you can see 45 is the root node, 30 is the left node, which has 30 is lesser than 40 and 50 is greater than 45. Again, this is the root node, this is a subtree, root node of the subtree, 30 is greater than 25. Left node should always be lesser when compared to the root node, right node should always be greater than when compared to the root node. Even here, see, 50 is greater than 40, 50 is less than 60. So, right node is always greater, left node is lesser compared to the root node. So, definition also says the same thing, binary tree in which every node contains smaller values in the left subtree and only larger values in the right subtree. Okay, this is the binary search tree where the left subtree is lesser value and right subtree has a greater value. You can see here left node value is less than or equal to root node is less than or equal to right node value. Okay, there are some certain conditions to follow while writing a binary search tree. All the nodes in the left subtree of any node contain smaller values and all the nodes in the right subtree of any node contain larger values. This is one property. Now, both the left and right subtrees of any node in the tree should themselves be a binary search tree. So, they are telling, so this is one binary search tree, this is one more binary search tree. Even the subtree is a binary search tree. Again, it has to follow the same property. Again, in the subtree also, the left node should be lesser compared to the root and the right node should be greater compared to the root node. So, again one more, the unique path exists from the root node to every other node. So, these are some conditions to be followed to create a binary search tree. Okay. So, next is, this is one more type of tree, this is a AVL tree. This is also, it's called as self-balancing binary search tree, but this is not there in the syllabus, but you can just go through this. So, what is exactly is happening here? This is a self-balancing binary search tree where each and every node will have a value. Okay. So, it is saying, it is the properties of this particular tree is self-balancing, it is self-balancing, every node has some value. Next thing is, each node stores a value called a balance factor. So, every node has some value. See, A has got 0, B has got 0, C is 0, D is 1, again E is 0. So, every node has a value. Okay. So, it is also called as a balanced factor, which is the difference in the height of the left. That particular balance factor is nothing but again the difference between height between the left tree and the right tree, left subtree and the right subtree. All the nodes in the AVL tree must have a balance factor of -1, 0 and 1, not more than that. So, this is the AVL tree. We do not have it for the syllabus, but you can just go through. Now, the most important part of binary tree. Okay. So, these are some certain operations when you are just creating a node is not enough. If you want to search or search for some element, what you have to do is, these are certain operations which we perform, that is pre-order traversal, in-order traversal, post-order traversal and level order traversal. These traversals are nothing but we are visiting the nodes or each and every nodes to perform some sort of operation. Okay, now, so this pre-order, I will just tell you what is in-order traversal. Just can you see this? The in-order traversal, what it does is, first it will visit the left subtree. First visiting the left subtree, then the root, then the right subtree. So, can you see here what is happening here? It is a tree of containing 7 of 7 elements. Now, what is the thing? This is the algorithm for in-order tree. Traverse the left subtree. First you are going to traverse the left subtree, then visit the root, then after that you are going to traverse the right subtree. So, for example, you have taken here, first what you are supposed to do? First you are going to suppose visit the left subtree. Left subtree is nothing but the D. So, first we visit D, so we write D. After D you are going to visit the root B. So, once you visit the B, then again you visit right node. So, first left root, then right. So, once this is over, again we go back to the left part. Okay. So, root sorry. After this you go to the root, then again this left part is over now. This left part is over, then you come here left side F. Okay. In-order traversal is nothing but you are visiting each and every node in an order. The order in the in-order traversal what we follow is, first we are visiting the left subtree, then the root, then the right subtree. This is the example what we have taken. The first we are visiting the left subtree. So, the most element which is there to the left is D. The D is visited, then P, then E, then go to the root, then visit. After completing the left subtree, go to the root. After that, okay. So, this is the pseudo code of recursive in-order traversal. So, you are supposed to write the algorithm for the recursive algorithm for all these traversal operations. So, for that I told you first you have to create a node. So, that is, this is what the class tree node, then you are taking one integer variable to store the data, then you are taking a left pointer, then right pointer to store the addresses. So, this is you are creating one tree node. After this, to call the in-order, void in-order tree node to the root, what you are supposed to do is, first we are going to check whether the root is equal to null, whether the root is empty. If the root is now empty, what you are doing is you are not visiting anything, you are just returning it, you are coming out of it. If the root is not empty, then you are going to traverse the whole tree using the in-order operation, that is in-order root left. First you are going to visit to the left node, then left element, then process the data, root data, then go to the right of the address. So, first go to the left address, then process the data, then go to the right address. This is in-order traversal. The next part is, okay. So the next traversal, we already saw the in-order traversal. The next traversal is pre-order traversal. So this pre-order traversal is, first you have to visit the root node, then we are going to visit the left subtree, then the right subtree. This is the algorithm of the pre-order traversal. So what are they telling? Pre-order tree, then visit the root node. So first we are going to visit the root node, then traverse the left subtree, then traverse the right subtree. That is, traversing is nothing but call the rep subtree. Now this example, in this example, what is it saying? First what we have to do is visit the root. So first you are going to execute A, after that you are going to visit B, then right child, that is C. One that is completed, again you have to come back. So this is the root, after that D, then E, then C, sorry, this is first A, then B. Now, okay, what is happening? First you have to visit A, after that left child is B, but B is the root for this two, D and E. So what you have to do? Visit root, come to left, D, enter D, then enter C. So this left subtree is complete now. Now you have to visit the root. The next root is nothing but A is already visited. So come to C. So after visiting the root, execute F, then towards right. So you can see here, this is left subtree, right subtree, A, B, D, E, C, F, G. This is the pre-order traversal. The next traversal, this is the pseudo code for the recursive pre-order traversal. Again, this is a code for creating, this is the code for creating the tree, that is int data, creating a tree node of class. Create tree node class, then you're creating a data of integer, then left address, right address. So this is the algorithm to create a pre-node. So in pre-node, void pre-node, tree node of root. If root is equal to null, return, or process. First thing what you're going to do in pre-order is you're going to process the data first, that is process root data. After that, pre-order the left subtree, then you're visiting the right subtree. So this is the pre-order traversal. Next is the post-order traversal. In post-order traversal, what is happening is, first you are going to visit the traverse the left subtree, then the right subtree, then the root, visit the root. This is the pre-order traversal, this is the condition for pre-order traversal. If you look at the diagram, first you have to traverse the left subtree. Left subtree is B, D, E. So first, again this is the root, then you visit D. First D is the last element which is towards the left. So visit D, then go to E, you are going to visit the right subtree, then the root. So this is complete now. After that, again you have to come to left. You should not go to the root. So execute F, then G, then C. So again now right subtree is completed. After once this is done, you have to visit the root. So that is D, E, B, F, G, C, A. So this is the post order traversal. So these are the three certain traversal operations which you perform using the binary tree. So there are like many, one more is there, that is this is the pseudo code for post order. Similarly, void post order tree node root. If root is equal to null, return. Post order root left, you are going to traverse the left side first, then traverse the right side, then you are going to process the data of that particular tree node. Okay, the last one is level order traversal. Level order traversal is using the breadth first. Usually it uses a queue, that is FIFO operation. What is happening here? It suggests that breadth of the tree takes priority first and then moves depth in first. In simple words, we will be visiting all the nodes present at the same level one by one. So what you are going to do is you are going to visit all the nodes based on the level. If you are visiting the first level, you are going to traverse all the elements in first level. If you are visiting the second level, you are going to traverse all the elements in the second level. So you are using FIFO, that is queue, to traverses. So that is why it is level order traversal. You are going to traverse toward the complete tree by level by visiting all the elements in that particular level. That is a level order traversal. You can see here. So first I will be visiting 1. So this level is over. Second, I will be visiting 2. Then after 2, one more element is there, that is 3. So these 2 elements I will visit. So 1 after 1, 2, 3. So this level is complete. After this, okay. Okay, after this 3, next level 4, 5, 6, 7. After 7, 8, 9, 10. So you are going to suppose, see last one, 1, 2, 3, 4. So every level you are going to visit all the elements that depends on that particular level, that is level order traversal. Okay. Okay, now this is binary search tree which you are going to, this is very important tree. This is the last part of your syllabus. So binary search tree is very important because it is very efficient in storing and searching the key values. Again, binary search tree is nothing but a binary tree. It is a binary tree with every node having 2 most children. So it can have more than 2 also. So at least 2 children have to be there at the end of the nodes. And the value stored in the left subtree of a node is smaller than the value stored something like this. So the left subtree is whatever the values which is there in the left subtree should have the lesser value when compared to the root, and the right subtree should be having the greater value when compared to the root. That is what it is here. Binary search tree, every value on the left subtree is less than the parent node, which is less than the right subtree value. This is a binary search tree. Now properties of binary search tree is nothing but it has unique values. So that is why, because it is not similar. So whatever the parent node is having, which is, it is greater than compared to the left subtree, and whatever the right subtree is having, which is greater than the root node. So always it is have a unique value. Each node will have a unique value. So no similar values are there. So this is because if there were 2 nodes with the same value, it would violate the binary search property. So violation of rules happens here. Next one is it is in sorted order. Just because I told now left is less than, sorry. Okay. See here in this example, the left subtree is less than the root, then the root is less than the right subtree. That is why it is in a sorted order. Everything is sorted. Whenever you find dissimilarities or similar values, or see 1 is less than 3, 3 is less than 6, 4 is greater than 6, sorry, 4 is less than 6, 6 is less than 7, so 3 is less than 8 and 8 is less than 10. So it is sorted value, it is in sorted way. Okay, this is the one more property. First one is each and every node will have a unique value, and all the values are sorted, and it is making it easy to search. Just because it is sorted, it is easy to search for the elements. So it is balanced tree. A balanced tree is nothing but which the height of the left subtree and the right subtree node differs by at most 1. The balanced binary search tree ensures that the search, insertion, deletion operations are performed in big O log n time complexity on average. So the maximum minimum value. So the maximum value in BST is the rightmost node, and the minimum value of the leftmost node is, so left subtree will have the lesser value when compared to the right subtree. So there is recursive in structure. So it goes on recursing. So this is the properties of binary search tree. So these are some basic operations on binary search tree. What are the operations? First let's see some basic terminologies of BST, that is children. So whatever the immediate successor of the nodes are known as children. Parents are the immediate predecessor of the node is called as binary parent, and root is the first node or the topmost node is the binary search tree is called as root. It is also known as the parent. Then leaf node is the last node which does not have any child. Okay, so these are some terminologies. So these are some basic operations of binary search tree. So that is creation, traversing. Creation is creating a node. Then traversing we have similar to binary tree. Traversing same pre-order traversal, post-order traversal and in-order traversal. Then we have searching of the element. To search the key element which is there in the tree. Then insertion and deletion. So in next class we will be seeing the implementation of these creating, traversing and insertion and deletion along with the code.